So today the first thing I will do is a discussion of the Bargmann invariants. These are expressions which are introduced by Bargmann in 1964 in the course of giving a new proof of the Wigner theorem on the way in which symmetry transformations in quantum mechanics can be represented. So the simplest non-trivial Bargmann invariant is of the following form. You take three generic unit vectors in your Hilbert space and you ensure no two of them are mutually orthogonal, and here is the definition of what is called the third order Bargmann invariant. It is a product of three inner products, Hilbert space inner products. You can see the way in which it is constructed that if you were to multiply psi 1 by some phase factor, e to the power I alpha psi 1, and leave psi 2 and psi 3 unchanged, the right hand side will not change, because in one factor psi 1 is on the left, in the other it's on the right. Similarly, psi 2 changing the phase of psi 2, no change in this expression, and also for psi 3. And in fact, you can see that it is really the trace of the product of the three corresponding density matrices, rho 1, rho 2, rho 3, rho 1 being psi 1 adjoint, and so on. So this Bargmann invariant is a ray space quantity. And it turns out that if the dimension of the Hilbert space is at least 2, then in general, this expression will be a complex quantity, so it will have a non-trivial phase. Now, I have drawn this figure here for you to see the construction I will now describe. So psi 1 is here. Here is where it projects to rho 1. Psi 2 projects to rho 2. Psi 3 projects to rho 3. And you draw a geodesic from rho 1 to rho 2. I can call it C12, but let me not clutter up this figure. Then you draw a geodesic rho 2 to rho 3, C23, and a third geodesic rho 3 to rho 1, C of rho 1. And then you draw lifts of these three geodesics at the level of the vectors. Script C12 running from psi 1 to psi 2, script C23 from psi 2 to psi 3, and back script C1. So when you do this, you can see that at the level of the unit sphere vectors, this thing C12 followed by C23 followed by C31 is a closed loop in B. And similarly, for the projection C12, 2, 3, 3, 1, the union of those three is a closed loop in the ray space. Now, yesterday I had written down a property of geodesics. What was the property? It said, using our definition of geometric phase, it said the geometric phase for any geodesic is 0. And that is the way in which we described that result in our approach. In Samuel and Bhandari's approach, it was expressed differently, but the content is the same. So if you repeatedly use that result, namely that the geometric phase is 0 for any geodesic, then it's a very easy exercise to show the following. The phase of this Bargmann invariant can be shown to be a geometric phase apart from a sign. It is the phase of delta 3 is the sum of 3 phases, the argument of each factor all added up, and that relation which I have referred to tells you that because each of these 3 legs of this diagram is a geodesic, it tells you that this first one, the argument of the inner product of psi 1 with psi 2 is equal to the dynamical phase for script C12, the curve connecting the two, script C12 being a geodesic at the vector level. So this is equal to phi dynamical of C12 plus phi dynamical C23 plus phi dynamical C31. And since the dynamical phases are additive, each one of these is an integral of that one form capital A along C12, C23, C31. So this is equal to phi dynamical of the closed loop script. So this is up at the upper part of that diagram. But you see, that is a closed loop. So there is no total phase. If you think of psi 1 as a starting point, the end point is also psi 1. It's the same vector. So total phase is 0. So you see immediately this is the negative of the geometric phase for what? For the closed loop or cyclic evolution defined by the 3 geodesics in the ray space. So it is a very elementary, very simple algebra. Ideas are very simple also. So this is the basic result, that these Bargmann invariants are very appealing, very simple to construct, but they have a lot of information in them, a lot of very interesting properties. And the basic result here is that phases of Bargmann invariants are, apart from a minus sign, geometric phases. This is the key result. Now this can be, so what is it of which it is a geometric phase? It is a geometric phase for a triangle in the ray space whose sides are geodesics. So we call it the geometric phase for a geodesic triangle in the ray space. So this is the original form in which the connection between these invariants and geometric phases was established. The last part of this course will be devoted to showing that this can be generalized in an amazingly rich way, but I'll come to that later. Now this is the first of a sequence of Bargmann invariants. This is a third order. You can define it for any order. Take any set of unit vectors psi 1, psi 2 up to psi n, and delta n will be the product of n scalar products. Cyclic. 1 with 2, 2 with 3, 3 with 4, and the last one will be psi n with psi 1. And the same, and you must assume in that case that no two successive psis are orthogonal to each other. Otherwise, you will get a 0. And then this argument can be generalized. So you see that for any non-trivial Bargmann invariant of any order, the phase of Bargmann invariants are always negatives of geometric phases. So this is a very simple derivation. Now I will start with some examples, some involving Bargmann invariants, some not involving them. So the first example which I want to describe involves a two-dimensional Hilbert space. Now, we have already seen two-dimensional situation in one context. As part of Berry's work, the behavior of geometric phases close to a double degeneracy. Then we can neglect all other eigenstates of the Hamiltonian, concentrate on just two states. And we saw how to handle it using Pauli matrices and using parameter space description, etc. So we have seen that. And that was in the context of the adiabatic theorem. It was Berry's original paper. There is a much older example in classical optics due to Pancharatnam, in which there is no adiabaticity at all appearing. It is in classical polarization optics. It was done in 1956. In a sense, this Pancharatnam example is purely kinematic. Of course, it was purely in a classical situation. So let me quickly describe this. So the physical situation you are considering is plane electromagnetic waves with a fixed propagation direction, let us say along the z-axis, with a fixed frequency. And what is variable is the state of polarization of each electromagnetic wave. So any electromagnetic wave, so remember throughout this example, the propagation direction is fixed to be the z-axis. So you can go to any one transverse plane and you can describe the electromagnetic field completely by giving the x and y components because of transversality. And I am using the usual complex representation of electric fields. So these are complex, and we are omitting this e to the power minus I omega t because frequency is kept fixed. So we can, so this is the electric field in a transverse plane, this being the propagation direction along z. So this is the xy plane. So for a given electric field, two things can be defined. Intensity I, which is apart from possibly some numerical factor, E dagger E. That is E1 squared plus E2 squared. And the other thing is the state of polarization. How is this described? As many of you should know, it is described by plotting a unit vector, which I am now defining, on the Poincare sphere. So the taus are the Pauli type matrices. The conventions in classical polarization optics are slightly different from those in ordinary quantum mechanics. So in order that you don't get confused, let me write here the tau 1 in this context is the sigma 3 as usually defined in the discussion of spin 1/2 particles in quantum mechanics. So when you do calculations, if you don't keep track of this difference in convention, you might get confused. So if you define E dagger tau 1, tau 2, tau 3 E divided by intensity for normalization, this is a real three-dimensional vector. It's a unit vector. And you get a point on the Poincare sphere, S2, and that describes completely the polarization state. So here in this, we are completely within this, what I call the HBR framework, with the dimension of H being 2. So this object B is S3, as we saw yesterday, and the ray space is S2 Poincare. Okay, so this we have seen it already. So now I want to show you, in this physical context, an example of this result, connecting phases of Bargmann invariants to geometric phases. What you do is that you choose 3 transverse electric fields. Call them E1, E2, and E3. And let us construct the corresponding Bargmann invariant, E1, 2, E3, and it is, for normalization, I divide by the product of the 3 intensities, E1 dagger E2, that is this factor in this example. The next will be E2 dagger E3, and the last will be E3 dagger E1. So this is the Bargmann invariant for this problem. By the way, this was equation 4.8, and this is 4.9. Now I just want you to appreciate some aspects of the right-hand side, and this is where Pancharatnam's deep insight and the new idea, concepts which he introduced come in. Let us keep the field E1, the amplitude E1 fixed. Then look at this first factor. If necessary, you can, in loose words, change the phase of E2. What I mean is you can stick a phase into E2, overall phase, so that this factor becomes real and positive. After all, the whole expression is a ray space type quantity. So putting phase factors individually into any one of these does not alter the right-hand side. You can see that. E1 comes with a dagger here and without a dagger there, and so on. So let us assume you adjust E2 for fixed E1, adjust E2 so that this first factor is real positive. All right? When you do that, you say, according to the Pancharatnam convention or the Pancharatnam definition, E1 and E2 are in phase with one another. The physical meaning is the following. That was his motivation. In such a situation, if you take a linear superposition of E1 and E2, you will get maximum constructive interference. That was the physical motivation. So let us assume you have adjusted E2 to make the first factor real and positive. Having done that, come here. Now you adjust E3 so that this second factor also becomes real and positive. If that is done, then you would say E2 and E3 are in phase with one another in the Pancharatnam sense, and therefore superposing E2 and E3 will lead to maximum constructive interference. Once you have done this much, there is no more freedom to play around with phases. And what you will see is that in general, E1 and E3 will not be in phase with one another, precisely because in general, this third order Bargmann invariant is a complex quantity. So 1 and 2 being in phase with one another, 2 and 3 being in phase with one another in the Pancharatnam sense will not tell you that 1 and 3 are in phase with one another. In general, and this was Pancharatnam's discovery, E1 and E3, the last factor in this product, is complex. It has a non-trivial argument. And this was his discovery. The in-phase concept is not transitive. 1, 2 in phase, 2, 3 in phase, 3 and 1 not in phase in general. And he went ahead and calculated the amount of this non-transitivity. That is what I will describe. So it is the phase of the third factor. And of course, this is the same as the argument of the whole thing, because the first two factors we have arranged to be real positive. And according to this general connection, this is the geometric phase of the following closed loop. And here I think I should draw a diagram. Let me use this for the moment. So let's say this is the, this is the Poincare sphere, or the Poincare laddu if you want. Here it is, not too bad. So the field E1, amplitude E1, superscript.
The lower part of that the line coming down.
Yeah, sure. This one.
Yeah,
Right. I should not have, unless I make it go out. It should not be there. I agree. So the polarization state of E1 is represented by some point N1 on the Poincare sphere. So this is S2 Poincare. Then the polarization state of E2 is represented by some other N2 on the Poincare sphere. And let us suppose the third one is here. So E1, E2, E3, through that formula defining the unit vector n, map to these 3 points n1, n2, and n3. And as I mentioned somewhat earlier, a couple of days ago, I suppose, or yesterday, in the two-dimensional Hilbert space case, geodesics in ray space, and ray space now is S2, geodesics in ray space are the same as geometric geodesics, namely arcs of great circles. So this would be the geodesic C12, this would be the geodesic C23, and this would be the geodesic C31. And therefore, this is a spherical triangle of which we want the geometric phase in this example. And this is now a matter of calculation, which is not very difficult. I just want to give you the result. That when you do the calculation, little bit of geometry plus algebra, you find that the geometric phase for that spherical triangle is exactly this solid angle, subtended by the triangle at the origin of the Poincare sphere. So this is what Pancharatnam had discovered in 1956. So I might just repeat. So this getting this result is not very complicated. I leave it as an exercise. So what he had shown, and incidentally, in the April 2013 issue of Resonance, it was devoted to Pancharatnam. And there is a very nicely written article by Rajaram Nityananda describing Pancharatnam's work. So those of you who may not have seen it, I urge you to look at that. April last year, Resonance issue. So the point of this derivation is to show how, in such a natural way, Bargmann's ideas lead to Pancharatnam's result. In Pancharatnam's paper, it is all classical polarization optics, no talk of Hilbert space or ray space. These terms do not appear at all naturally in his work. And the focus of the work was to show, if you introduce this concept of two electric field amplitudes being in phase with one another, that property does not have the transitivity, does not obey transitivity law. 1 and 2 in phase, 2 and 3 in phase, 3 and 1 generally out of phase. By how much? By half the solid angle of the corresponding geodesic triangle on the Poincare sphere. So this is the first example I wanted to show you. And another way of appreciating the connection between the Bargmann invariant and the Pancharatnam non-transitivity is the following. It is not necessary to do any calculation to see that the Pancharatnam concept cannot be transitive. It is obvious upon inspection, because once you know the existence of this Bargmann expression, and you know that in general for dimension h at least 2, in general this is complex, you know that transitivity cannot be there. That is what no calculation, because if this is in general complex, and you in the most general quantum mechanical situation also, if you adjust phases so that this first factor is real positive, and then you adjust psi 3 so that this factor is real positive, you are stuck. This you cannot tamper with this third factor. If the left hand side happens to be complex to begin with, the phase of that must show up in the third factor. That is the main thing. Okay. So the value of connecting these two ideas is to make one see that the fact that it is not transitive is trivial. It is obvious upon inspection without any calculation. But if you want to know by how much do you lose transitivity quantitatively, then you have to do some calculation to get minus half of the solid angle on the Poincare sphere. Okay. Now my next example, any quick comment? Yeah.
I mean, if it is not too much demand on your time.
No.
See, there this triangle,
Yeah.
this closed triangle, you have inserted to a closed thing.
Yeah. Yeah.
But then here you talked about, psi 1 and psi 2 being, E1 and E2 being in phase, E2 and E3 being in phase.
Yeah.
Now that also can be imagined as a lift there.
Yeah.
In which case what you have in B space, this will not be a triangle.
Well, actually it is, because E1 is an example of a psi 1. Yeah. E2 is an example of a psi 2. E3 is psi 3. I don't have some E3 prime in this discussion.
I
in
know,
that spirit, yeah.
If E3 had to be in phase with psi 1, then that will give you a.
Yeah.
See,
right.
You have to close it. You cannot just leave it with two arms.
Yeah, you must. This is closed to begin with.
Yeah.
Its lift, if it is closed, the total phase is 0. The calculation of geometric phase simplifies. There's only one term. The lift up here could be open. Then the calculation of geometric phase will have both terms. There will be a total part and a dynamical part. That is correct. So it does not mean that the lift of this necessarily has to be closed. It doesn't mean that. But I have chosen it in this case in that. Yeah. That's.
No, I was
Yeah.
going to say that it will open
Yeah.
exactly the amount
Yeah,
equal
yeah.
to the geometric phase.
Yeah, correct.
I mean, see there, you make, in this lift, total phase is 0.
Yeah.
You can lift it in such a way that
Yeah,
the
yeah.
dynamical
Yeah,
phase
yeah.
is 0, so that the
Yeah,
total
yeah.
phase is the geometric phase, and that will be the exact
Correct.
opening, and that will
Yeah.
be the transitivity failure.
Correct. Perfectly right. And since you have mentioned it, let me just make the following comment. Our general definition of geometric phases for curves in ray space which don't have to be closed was this. And as we said yesterday, to calculate the geometric phase for a curve in ray space, you may choose any lift you like up above. Doesn't matter what script C you use. Having chosen a lift, you calculate this part, you calculate this part, and take the difference. This difference does not depend on which lift you used. Therefore, using this freedom, you may choose a lift in which this is 0. You may choose a lift in which this is 0, but the difference you cannot tamper with. That is all. So there's infinite freedom in the way in which you make the lift from ray space to vector space. And since, though I mentioned it yesterday, the connection between the two ways of proving Berry's original result is of this nature. There is freedom in the way in which you present the proof. That is what I exploited in first giving a simplified version of his result and then the way in which he originally did it. Okay. So now, in the notes, the next topic I have discussed is the case of 3-level systems. But I decided that I will not describe it now. If there is time on Saturday, I will go into it, but I will go on to other things now. In any case, the notes will be hopefully given to all of you very soon, so it's okay. Now, one other example of geometric phase, just so that you feel more and more at ease with all these concepts, is what you might call a toy model. A toy model, an example of a geometric phase in which Bargmann invariants don't enter the argument at all. So my example B was this case of 3-level systems, a degeneracy in 3-level systems. In the spirit of Berry's original work, I will not present it now. What I will show you now indicate is what is called the while phase as a geometric phase. So this is, as I said, it's a toy model, but I will not give you all the details. I will ask you to do the calculation. The Hilbert space here is the set of all square integrable functions in one dimension. So it is infinite dimensional. So the space B and the space ray space are all infinite dimensional. And the analysis is of the standard canonical commutation relation. Equations from 410 to 428 are connected with that other second example, which I will not go into now. So this is the Heisenberg commutation relation for 1 degree of freedom. And as you know, in exponentiated form, using only unitary operators, it can be written in this way. And this is called the while form. this is equal to, now I will put h bar equal to 1 to avoid complication in expressions. So this is the while form of the canonical commutation relation. And this phase on the right, it is really a reflection of this non-commutativity. This is called the while phase. What I would like you to appreciate is that this while phase is actually a geometric phase. And as I said, in this statement, there is no Bargmann invariant needed. It's a very simple exercise. I want you to please do it. So what I will indicate is the following. Take any vector psi 1 in the Hilbert space, any vector psi 1. Now, you can imagine going from psi 1 to this vector, which I call psi 2, by a gradual evolution. What I mean is, you put in a parameter s and let it run from s equal to 0 to s equal to a, whatever the a is. So you have gone from a vector psi 1 to a vector psi 2 by Schrodinger evolution. The Hamiltonian is the momentum operator. Having come to psi 1 to psi 2, you make the next step. On psi 2, you apply this evolution, parameter going from 0 up to b. Let us say the result is psi 3. Then on psi 3, you apply this evolution. Then it is psi 4. And last leg is you apply this last one on psi 4. In every case, I mean you put a parameter s and let it run from 0 up to the appropriate value in that factor here. So here is a evolution, you can say, which takes the any arbitrary psi 1 in the Hilbert space, first to psi 2 by this evolution, next psi 2 to psi 3 by this kind of evolution, 3 to 4 by this factor, 4 to 5 by the last factor. And you know from the commutation relation, this while form of the commutation relation, you know that psi 5 differs from psi 1 by a phase, namely the phase on the right. This is exactly like what you were saying in the other example. And so you can see, now you can ask for this evolution, which is obviously closed at the level of race space, you can ask what is the geometric phase. And you will see very quickly, this I will leave it as an exercise for you. The total phase is trivial. It is the phase of the inner product of psi 1 with psi 5, and that is minus AB. And then you can calculate the dynamical phase. It will be contribution of 4 parts from this evolution, then from this, then from this, then from that. And when you do all the calculation, it turns out, and this I leave as an elementary exercise, the dynamical phase is minus 2AB. And therefore, the geometrical phase for this cyclic evolution in the race space is exactly phi total minus phi dynamical. It is AB. So this is, apart from sign, it is the while phase in the original commutation relation. So this is a simple toy exercise to show you that even the Heisenberg commutation relation of quantum mechanics, which is basic for quantum mechanics, it has this meaning in the language of geometric phase. That is all I need. Okay? All right. So now my examples are finished, and now I go on to.
Why did you emphasize twice that this has nothing to do with Bargmann invariant?
I didn't use it here. That's all. I just looked at it directly as a evolution given explicitly.
But,
Continuous
they
evolution.
Also, I mean, will it be
Yeah.
wrong if I add that it won't actually computed the Bargmann invariant, what will get precisely that answer.
Yeah, you are correct. Yeah, yeah, right. Because all the that is also
there
true.
are 4 states.
Yeah, yeah.
So you can take the bottle
Yeah,
and meal in
yeah,
the,
right.
keep it plain.
Correct, correct. So you do it both ways. For
That will be the area.
yeah, yeah, yeah. This AB is the area. So you please do it in both ways. Regard it first as a Bargmann invariant independent derivation, and second as a Bargmann invariant being exploited. Do both.
Because Hassan and company seem to be interested only in that kind of this area business.
Which area?
Finally, they want
Yeah,
to
yeah,
get this geometric tensor where
Yeah,
essentially the 2 form will give you these areas.
yeah, yeah. Okay, fine. I'm coming to the area idea very soon. Very soon. Okay, so this is done. So now I can actually remove this diagram. And now I go to the next major part of this set of lectures, the next section in the notes.
When you say the dynamical phase is 2AB, what the beginning state we had?
Ah, right. So it is independent of psi1. Whatever initial state you choose, the geometric phase for this sequence of evolutions, continuous evolution, closed in the ray space, it does not, the geometric phase does not depend on psi1 at all. That is special.
Geometric phase, yes. Dynamical phase.
Dynamical phase also is independent. It does
They
not.
had started with vacuum.
Yeah, yeah.
I was under the impression that for vacuum the dynamical phase will be 0.
Not in this example. If you do this result that the dynamical phase is minus 2AB is correct, not depending on choice of psi1 at all. Okay, so this is a nice exercise. It is simple enough that you can do it fairly easily, but it has all the elements of the subject in it. That's why I thought I should give it to you. All right. So I have brought in Pancharatnam's work, I have brought in Weil's work, and now I go on to more mathematical topics. So this is what I have called second mathematical interlude. I hope you find this interesting and informative. See, in the first mathematical interlude, that was section 3 of my notes, I had described the following things. This HBR framework for quantum mechanics for geometric phase calculations or ideas, and as Simon said, it has a much wider meaning. Then we talked about how length is defined for curves in the ray space, how you get geodesics out of this length definition, and given a geodesic, how to lift it up. The freedom, the possibility and the freedom of lifting geodesics from ray space to the vector level. And then we looked at this special one form. Maybe I might just write it here and keep it there. A one form on the space B. Now I want to describe to you some more aspects of this kind of mathematics, this geometry, so that you get a better understanding of all these spaces and of objects which are defined on those spaces. I will not give proofs or derivations. I'll indicate what is important and leave it to you to work things out. At this point, I might mention two things. Is Krishna Kumar here? Ah, you are there. Okay. I have a little job for you for tomorrow. When I was in Princeton, of course, I was greatly impressed by Bargmann. I attended his course of lectures for a whole year. So I felt sufficiently familiar I was trying to read at that time these differential forms, trying to understand them. What, 50 years ago? I'm an old man. So I went to him once and said, can you tell me something about what differential forms are? I think I was trying to read at that time this small book by Flanders, Harlan Flanders. So he just looked at it and he said, oh, what are differential forms? Just antisymmetric covariant tensor fields. Now, his background was that he had been an assistant to Einstein in the 1930s. So that is what he told me. Then this is where Krishna Kumar comes in. If you can get hold of this book of Hermann Weyl, the Dover edition of Space, Time and Matter, and go look at the preface. In that preface, I think he says that in recent times, these mathematicians have started introducing definitions and notations. He expresses very strong disapproval of this formal language of mathematics. He says they disturb the peace of mind of the working physicists, things of that kind. And an emphatic protest must be lodged against them. He was dead, huh? Hermann Weyl, 1920 or something like that. So by tomorrow, you please bring it. But when you bring those sentences, don't put the idea of food into it. So you please search. So you please trace that sentence. And it's, if you can print it out.
This lecture, you wanted everything to be understandable to everybody.
Yeah.
Now you have made something which is understandable only to you and Krishna Kumar.
And to you. Yeah. So I just want you to see what he has said in that preface to that book, Space, Time and Matter, I think, which just shows what Bargmann said to me in 1964, what Weyl wrote earlier. Times have changed. That is the main thing. And the people with the older training, they were resistant to new mathematical ways of doing things and so on. So you can imagine my plight being 75. So now I hope that you will have a better experience in life than me. I would like to give you a little introduction to some of these powerful mathematical ideas and techniques, and you must learn much more on your own. So I want to describe these things at two levels, at the level of vectors, unit vectors, and at the level of race space. Incidentally, I must also mention this paper of Samuel and Bhandari. They never use the idea of this unit sphere, normalized vectors. They feel more comfortable working in the full Hilbert space. The only thing they say is they will work in the Hilbert space without the zero vector. That they will omit, because zero vector, it's not important, but they explicitly work in that framework. So when you try to relate what I am describing with the discussion in Samuel and Bhandari, please watch out. This space does not enter anywhere. In its place, everywhere it is Hilbert space, full Hilbert space, minus 0. Okay, just a passing comment. So we have defined for a Hilbert space of dimension, complex dimension n, this is of real dimension 2n minus 1. And we have seen this in examples also. So you remember where this definition was given. Now, if you take a point in this space B, it is a real manifold of dimension, differentiable manifold of dimension 2n minus 1. At every point of B, there is a linear vector space called the tangent space to B at the point psi. Okay. So how is this to be pictured? I will not draw a diagram. You can see it in your mind. At every point psi, what does a tangent space consist of? You imagine smooth curves in B, parameterized, let us say, by parameter, passing through that point psi at parameter value 0. And for each such smooth curve, you evaluate the tangent vector at the origin. The tangent vector to a smooth curve at the point where it passes through psi. The set of all these tangent vectors is the tangent space to be at the point psi. Okay. So, huh?
It's always non-compact.
Yeah, we will see. Now, of course, here complex things are involved. Psi is a vector in a complex vector space. But take instead of B, take S2, the sphere S2. Huh? At any point of the sphere S2, what is the tangent plane? So use the same definition. You must imagine smooth curves on S2 passing through your chosen point and calculate the tangent to each curve at that point. What is the result of that calculation? You get an entire plane R2, set of all vectors in 3 dimensions. You can picture it in 3 dimensions. Set of all vectors in 3 dimensions, tangent to S2 at that point, at the chosen point. So at each point of S2, you have its own tangent plane. Okay? So here, this is something that you can easily calculate. The tangent to B at a point psi in B consists of all vectors in Hilbert space such that the real part of the inner product between psi and phi vanishes. I think you know exactly why this condition comes. What is the reason? Where does it come from?
This norm is 1.
Exactly. Any curve, parameterized curve, psi of S, lying in B, passing through psi at S equal to 0, it has to be a unit vector. So you take the condition unit norm of psi, differentiate it with respect to S and put S equal to 0. Then you will find if the tangent to psi of S is phi, you get real part of this inner product is 0. So remember, in this expression, psi and phi are not on the same footing. Psi is a unit vector. It denotes a point on the space B. Phi is a possible tangent vector to some smooth curve on B, passing through psi. So you can see that always in this expression, psi is a unit vector, phi is any vector of any length in the Hilbert space for which this condition is satisfied. Okay? All right. So this you can see that this is a real linear space of dimension 2n minus 1. Same dimension as a B itself. This is exactly analogous to this, what we just said a few minutes ago. The tangent space to S2 at any point of S2 is a 2-dimensional plane. The dimension of that plane is the same as the dimension of S2 itself. Now, all right, so this is a real linear vector space. Its elements are vectors in the complex Hilbert space obeying this restriction. So why is it only a real linear vector space? Suppose phi 1 and phi 2 both obey this condition. Real part of psi phi 1 is 0, real part of psi phi 2 is 0. If you were to take a complex combination of phi 1 and phi 2, you would destroy this condition. If you want to preserve this, you have to take real combinations only of phi 1 and phi 2, and such combinations will also belong to this tangent space. I hope this is clear. Now, there is one subspace of this which is very easy to picture. Maybe I can use this diagram here. I can do one more thing. Let us suppose this is a point rho here and psi sitting on top of it. So let us say this psi is the one I am referring to in those equations. So tangent vectors to B at this point are various vectors in Hilbert space pointing in different directions, obeying that condition. Now, each one of these was the tangent to some smooth curve passing through psi. Suppose you imagine a smooth curve in the space B passing through psi, which is totally contained in the fiber, moving only through the fiber. Such a thing would be also permitted here, and that is called the vertical subspace of this, and this, it consists of all pure imaginary multiples of psi. It corresponds to our curve being along the fiber. Okay? So the fact that this is by inspection, a subspace of this is trivial, because if I take phi equal to I A psi by A is real, the real part of this is 0, right? Because the scalar product will be I A, and A is real. So this subspace is easy to picture, easy to define. So I will write here again. This is something available at every point of B, and this is called the vertical subspace of the tangent space. Vertical because in that picture you can see it corresponds to moving along the fiber. Okay. Now, you remember this one form, capital A, which I have written here in somewhat symbolic way. This was defined earlier. Now, what is the general meaning of a one form on any manifold? Any one form on a manifold consists of a linear functional on every tangent space. It is something which is defined at each point of B in this example, and a one form at each psi is a rule which will map tangent vectors to real numbers linearly. So that's what is the meaning of the word linear functional. So let me just say how it is done for this particular one form. The case of that particular one form, what you need to, the ingredients needed are the following. You are working at a certain point of the space B, and you are looking at a particular tangent vector at that point. Then here is what defines a one form. The one form A at the point psi consists of a rule to map every tangent vector to a real number in a linear fashion. And for this particular thing, it is exactly equal to imaginary part of psi phi. Remember, the real part is 0 because phi is a tangent vector. Or it can also be written as minus I psi phi. So this is the point-by-point definition of the way in which this one form acts. In other languages you may be more familiar with, we might say phi is like a contravariant vector. That's the same thing as a tangent vector. A one form is more like is a covariant vector. It is also called a cotangent vector. So you can I'll write this here. Phi in this context, phi is a tangent vector at psi, and a psi is what is called in this differential geometric language a cotangent vector at psi in B. The cotangent vector is nothing but a linear functional on tangent vectors. Something which assigns to every tangent vector some real number in a linear fashion. So this is how the one form A is defined. This particular one form. Okay. You can have other one forms as well of various with various definitions. So this particular one form A is defined in this way. Oh. Now, given a one form A, this A, there is a subspace called the horizontal subspace. It is a subspace of the tangent space on which A psi vanishes. And so, in this case, you can see the horizontal subspace at B consists of all vectors in the tangent space such that A psi of phi is 0. But what does that mean? If A psi of phi is 0, it means the imaginary part of the scalar product is 0. But you already know the real part is 0. So it means it amounts to psi of phi equal to 0. As a Hilbert space vector, the horizontal subspace at each point of B consists of all vectors in Hilbert space orthogonal to psi. Okay? So what I think you should appreciate is the tangent space is a real linear vector space of this dimension. You cannot regard it as a complex linear space because this condition would be violated. The horizontal subspace, however, is also a complex vector space because it is a subspace of Hilbert space orthogonal to psi. So this is a space, linear space of complex dimension, how much? All vectors orthogonal to psi. N minus 1. Complex dimension n minus 1, real dimension 2 times n minus 1. And now you can see, here is the vertical fellow, here is the horizontal fellow. You can see the tangent space at each point of B has a vertical part, has a horizontal part, and the full tangent space is the direct sum of these two. Okay, maybe I should have written here complex dimension n minus 1. This had a equation number. Somewhere I should put an equation number. So actually you can go back to this first equation defining the tangent space. If this is the definition of vectors in the tangent space, phi inner product psi should have no real part. What is the most general way in which this can be achieved? If phi is a pure imaginary multiple of psi plus something perpendicular to psi, That is, take any phi obeying this condition. You can, in the Hilbert space sense, decompose it into a component along psi and a component perpendicular to psi. This is always possible. The part parallel to psi must have pure imaginary coefficient, so that the real part here will be 0. Now you look at this, you see this is the vertical component of phi, this is the horizontal component. Of course, all this definition of horizontal component is with respect to the one form A which we are dealing with. So may I repeat, tangent space is an intrinsic concept. At each point of the manifold, it is a well-defined linear vector space, real linear vector space. Vertical also is intrinsically defined. It is a part of this. Horizontal subspace at each point requires the use of some one form. And here we are using this one form. And it is that part of the tangent space over which the one form vanishes. Okay? So these are very important notions. In this very simple case, this is how it all works out. All right. Now I come, I'm still working on B, and one last construction on B. I'll just show it to you.
What is the dimension of the article?
Dimension of vertical space. Well, you tell me. What are the elements of the vertical space? No, no. More.
Defining vertical space that is perpendicular to
Yeah, yeah.
the E. The
Huh?
horizontal one.
No, no, no. See, the vertical subspace is defined right away. You don't appeal to any one form or anything like that. If you want real part of psi, phi inner product to be 0, and if phi is proportional to psi, what is the form of phi?
Some I
I, A, psi, where A is real. That's the only thing they can change, vary. So the vertical subspace is a one-dimensional vector space.
complex dimension.
One real dimension. Yeah, A is a real number, no? Of course, that is because here the fiber is U1, it's one-dimensional. This is a case where each fiber is one-dimensional. So the vertical space is also one real dimension.
This is 2n minus 2, real, horizontal.
Yeah, yeah. 2n minus 2 or complex n minus 1.
Now,
Everything is clear, no? Very good. Okay. Now, I said A is a one form on B, on the manifold B. So that is what is defined here. At each point of B, this equation tells you how A at that point acts on tangent vectors there. This is its action. And as I said, when you study general relativity, you talk about covariant vector fields, contravariant vector fields. A one form is really like, as Bargmann said to me, it is a covariant vector field. But in this language, we call it a one form. It's also called, as I said, at each point, it defines a cotangent vector. Given that there is an object called the differential of A, it is written as d of A, and it is a two form on the manifold. This concept of d here is the same as in vector analysis, the curl operation. So this is an antisymmetric differentiation, if you like. So if A, you picture it as a covariant vector field, this is a second rank antisymmetric covariant tensor. That is what the d operation does for you. Okay? So this is like the curl operation. Or in the language of electrodynamics, if you like, if vector potential is a mu, that's a covariant thing, then what is the field strength? It is the antisymmetric derivative. No? Covariant, second rank, antisymmetric. This is the description in conventional, in language you might be more familiar with, of the exterior differentiation operation. Exterior differentiation means take the partial derivative and antisymmetrize everything inside. That is what it involves. So dA is a two form. It is the result of doing this antisymmetric differentiation or the curl operation. And in this spirit, how is dA actually defined? This is very important. What we now say is that at each psi in the manifold, we want to define, we want to say what is the curl of, what is the exterior derivative of A at that point. Well, just as A was a linear functional on tangent vectors, its exterior derivative is a bilinear functional on tangent vectors. So you must take two general tangent vectors at B, and then you must say the value of dA at psi evaluated for the pair of tangent vectors phi and phi prime is so much, whatever it is. I'll write what it is. But the important thing is it must be linear in phi, it must be linear in phi prime, it must be antisymmetric in phi and phi prime. The antisymmetry is the crucial idea. And a little bit of calculation, which I am not going to show you here, leads to this result. I will give you some pictorial idea how you can work your way to this result. But there it is. Okay. So I am making a claim. I am not giving all the proof for you. For this one form on the unit sphere B in Hilbert space, its exterior derivative is that two form. And there is no ambiguity in this. Starting from here, in a systematic way, you can arrive at equation 5.5. I am not giving the proof. I want you to, you have to get some amount of expertise in this kind of manipulation. And you can see that this is a real bilinear antisymmetric functional on pairs of vectors, which is what a two form has to be. Remember, phi and phi prime are vectors in Hilbert space which belong to the tangent space. Okay. So there will be a vertical component, there will be a horizontal component, etc. But from Hilbert space scalar product properties, you know this is antisymmetric in phi and phi prime, because interchanging phi and phi prime means taking the complex conjugate of the scalar product, therefore changing the imaginary sign of it. So this has the required antisymmetry. All right. So this was some amount of machinery, geometric machinery associated with the space B. So that's at the vector level. Now I want to do analogous things, almost as much, but not quite as much, at the level of ray space, the necessary geometrical objects. But if at this point you have some question or comment about this, it would be a good point to stop. Any comment or anything? Okay. If not, well, if something comes to your mind later, we will take it up. Now, what are the objects that I need for our purposes associated with the ray space? Well, we know that this is what is called the complex projective space of complex dimension n minus 1, that we know. Now, the thing that is given to you is this projection from vectors to points in the ray space. That is part of the mathematical framework. So now we have to ask, if I take a point in the ray space, just as I took a point psi in B, now I take a point rho in R. And I can imagine that this rho is in fact the projection onto some vector psi. But of course, this psi is not unique. For a given rho, I can take psi to be anywhere on the fiber sitting on top of rho, because that means only changing the phase of psi, and in psi adjoint, that will go away. So now you ask the question, how shall we define the tangent space to the ray space at any point of it? Well, how should it be defined? You must imagine drawing smooth curves in ray space, parameterize them in some way, make sure that they pass through the point rho you are working at, and calculate the tangent to that curve. Same principle as in the case of B. All right. And now, this result is very nice, very appealing. I will write it first and then maybe describe a little bit. Now, this B is not a curly B. Maybe I should have used some other symbol, but in our papers we have used it, so I use the same. Now, remember, the ray space is a set of operators, projection operators. So, unlike tangent space to B at each point, which consists of some set of vectors in Hilbert space, now we will be getting the tangent space elements to be certain operators on Hilbert space. What are the properties? I will write them first, and then I will indicate where they come from. This is the anti-commutator. Now, this is part of equation 5.6. Let us see very quickly where each of these would come from. What are all the properties of a pure state density matrix? Can somebody tell me one by one, what are the properties of rho? 3 properties. What are they? Right, let me write them one by one. Hermitian. Yeah? Huh? Pure state. Rho squared. Rho squared equal to? Rho. Okay. All right. So these are the defining properties of a pure state density matrix. Every point in R is some rho obeying those 3 conditions. All right. Now, suppose I take a curve lying in the ray space, passing through a given rho at s equal to 0. All right. So I will say rho of 0 is this rho. Now, take this equation. It has to be obeyed by rho of s for all s. So take its derivative with respect to s and then put s equal to 0. Let me call that the operator B. What are the properties of B which follow from here? Hermitian. What property follows from here? Huh? 0. Because the derivative of 1 is 0. And what comes from here for B? This would say rho of s whole squared equals rho of s. All right? Differentiate with respect to s and then put s equal to 0. And what do you get? You get exactly this one. Right? Rho squared of s, rho of s squared, when you differentiate and then put s equal to 0, there will be 2 terms. Rho b plus b rho. And it must be equal to the derivative at the right. So you get exactly this relation. So the tangent space to row space, to race, my God, to race space at each point of race space has a very interesting and nice structure like this. All right? It has to be described in terms of operators in this way. Okay, these are the elements of the tangent space to R. But it now turns out, and this I will write it and then maybe try to prove it. Every such B can be uniquely written in the way I am now writing. So this is all part of equation 5.6, second line. It turns out that here you are in the race space. Choose some psi sitting on top of rho. You can change the choice of psi as you wish, but for the moment, choose some psi. Then all the tangent vectors down here are describable in terms of objects here in the way I have written. Every B corresponds to some Hilbert space vector chi orthogonal to psi. First, let us see that all these conditions on B are obeyed. Is the hermiticity obeyed? Oh, something was missing. This is obviously Hermitian, right? Chi psi adjoint, which is an operator, it's not an inner product, plus psi chi adjoint. This is Hermitian. Is the trace of this 0? This is an operator on Hilbert space. What is the trace of this? Yeah. Therefore, this has no 0 trace. So this condition is satisfied. What about this one? Let us just see. It's very, very interesting. We want to B rho anti-commutator we want to calculate, right? Now, I say that B is equal to this. So let us calculate chi psi adjoint plus psi chi adjoint rho. What is rho? Psi adjoint. This is the first term in this anti-commutator. Plus, what is the next term? Right? This is the anti-commutator of B with rho. Now, see how many things just disappear. This is 0 because chi and psi are orthogonal. This is 0 because psi and chi are orthogonal. What about this fellow? Psi is a unit vector. So what is this one? Chi psi adjoint. And what is left here? Psi chi adjoint, which is B. Right? So the point is that here is the direct definition of the tangent space to race space at any point of it by saying it consists of all Hermitian traceless operators on Hilbert space obeying this algebraic condition. This is the condition where rho becomes relevant. Where are you in race space? And I'm claiming that here is the most general expression for each such B. So every tangent to R at rho corresponds in this way, in a unique way, to some vector chi orthogonal to psi. The two are one-to-one related. Remember, what is the dimension of all such chi? In the complex sense, it is n minus 1, the orthogonal complement of psi. This is a complex space of dimension, complex dimension n minus 1. So what we see is that it is possible to describe the tangent space to race space in a very nice way by this expression. Okay. I will go a little beyond 1 like yesterday. I also, now I leave this as an exercise for you to show the following. It is really quite pretty. I'm not going to use this anywhere, but it is nice for you to see how to show this. If you take I times commutators of rho with all Hermitian operators on Hilbert space, you will get results which obey all these conditions. At least 2 of them are very easy to see. Hermiticity is obvious. If rho is Hermitian, k is Hermitian, and I have an I, the whole expression. Commutator is anti-Hermitian, so I makes it Hermitian. So B is certainly Hermitian. Trace B equal to 0 is trivial because you have a commutator. The third one, you please work it out and see why this is satisfied. So every vector, tangent, everything, every element in the tangent space to ray space can be described in this way by defining properties, can be described in this way by explicit display of such vectors, and it can also be described in this third way, and they are all equivalent. And to see the equivalence, one can in fact show that the k that you must use in this alternative definition to get the earlier definition is this expression. Okay? Same chi and psi are involved.
Matrices actually have a form of a sigma 1 or a sigma. They look a bit like sigma matrices.
Sort of, yeah, you're right. Yeah. Wait, this one,
Even
sigma 2.
This one looks like sigma 2, but the one above that looks like sigma 1.
This one?
No, the one above that.
Yeah, this looks like sigma 1. Right. You can, good point, nice observation. You can play around and see if you can get something out of it. Is there something in which sigma 3 plays a role in that spirit? You can ask. I don't know. I don't know the answer to that question. So, good question. I just want to say, please understand, we have tangent space to B at points in B that we have used here to define how the one form acts. Now, this is a description of tangent vectors to ray space. Very different mathematical object, and there are all its properties and definitions. All right. So, what can I rub out? Yeah, I think this I can rub out. Those equations I will need. Now there is a very important operation in theory of manifolds, differentiable manifolds, which is called the pullback operation. So I'm not able to give all the details of it. The important thing is that we are given a projection operation which takes points in the total space into, maps them to points in what is called the base space. So in this context, the ray space is the base space, and the unit sphere in Hilbert space is the total space. And we have the projection like this. Now it's a general rule, and this you will see in Riemannian geometry and such things also. Covariant.
Can you totally avoid bundle?
Not totally.
No, because if B you have always what have you written?
Total space. Huh? No, total. Yeah, sorry, I'll write it. It is the total space. Now, it is a fact which you can see in books and learn that whenever there is this kind of projection map from something larger to something smaller, covariant tensors, covariant vectors, covariant second rank tensors, covariant third rank tensors, etc., on the lower thing can always be pulled up to the upper space. In more explicit detail, if I give you a covariant vector field in the base in a unique, well-defined way, I can create a covariant vector field on B from that. And that is called the pullback of this fellow. If I give you a second rank covariant tensor field, I can jack it up and produce a second rank covariant tensor field on B. Contravariant tensor fields cannot be handled in this way. So this is called the pullback operation, and so it is special to covariant, and it is written as pi star. Okay. Now, I think one place where this word would not be used, but the idea would probably be well described is this book of Schrödinger, written in the 1940s or early 50s, called Space-Time Structure. It's a very, very beautiful book, very nice language, very thin book, 100 pages or something. Our generation, we had used it years ago. If you have not seen it, you must. It is, I think, it was reprinted some years ago by Cambridge University Press in a series called Canto series. Canto. So it may still be available. It is well worth possessing. So this special behavior of covariant tensor fields, objects, as against contravariant, for which this thing doesn't work, it is described, I would think, in that book. But in any case, you must get hold of this concept. So the situation, the relevance of this comments here is the following. Now, on the space B, we have the one form, capital A, which is there up on the board. And I have described it in great detail earlier. And then we have its exterior derivative, its differential, dA, which also I had written on the board earlier. So to repeat, at each point of B, A acts as a linear map of tangent vectors at that point into real numbers. dA acts as an anti-symmetric bilinear map of pairs of tangent vectors into real numbers. This is all at B. Now, it turns out, this is a secret, there is so this is called a two form. In the old language, covariant tensor antisymmetric second rank. That is what it is. It turns out that there is a covariant antisymmetric tensor of second rank, namely a two form, on the lower space, which, if you use this pullback operation, gives you the two form on the upper space. So we can say that, on the other hand, there is nothing at the level of ray space which can be pulled back and would give you A. So there's nothing from which A comes, but dA comes from something. This is a very big difference between the two. So we say, another way of expressing it is, A is not projectable from total space to base space. dA is projectable, it does project onto something, and it is in fact the pullback of that thing. Okay, so that is the relationship. So now you remember that okay, yeah, I know now I have to rearrange my pages a little bit. I will do it in a nice way now. Let me just show you, not derive, but show you what is this 2 form on the ray space, which is sort of lying deep underground below this dA. Well, if it is a 2 form, it has to be defined by saying that it acts in such and such a way on pairs of tangent vectors. It has to be antisymmetric, it has to be real valued, and linear. So here is the
Why is there no one form?
that I will be able to show it to you tomorrow. So for today, the message is there is nothing from here. A is not projectable. Okay, that is the key thing. So let me show you what this thing looks like. You take any point rho in the ray space, write it as psi adjoint for some psi lying on the fiber. You take 2 tangent vectors to ray space at that point, say B and B prime. So B is Hermitian, traceless, and obeys this condition. B prime is Hermitian, traceless, obeys the same condition. Both of them are like that. So now I have to tell you this 2 form rho, what does it do to a pair of tangent vectors at rho? I have to specify the value of this as a real number, linear in B prime, and antisymmetric in B and B prime. If I have done that, I have given you what omega is. And here, so these are not things I have time to derive, but I think you must appreciate how everything hangs together. The commutator of B with B prime enters, I should have put B prime B. It is antisymmetric, so the sign is relevant. So here it is, and it is also 2 times imaginary part of chi with chi prime. Inner product of chi prime with chi. What are chi and chi prime? They are the way the vectors out of which B and B prime are built by this rule. Okay? So I know that there is fairly elaborate machinery, but I want you to slowly get adjusted to it. We are describing tangent vectors to ray space in different ways. 1, by a set of algebraic conditions. 2, by explicit construction in this way. And now we are using this construction to say exactly what this 2 form is. So this is equation number 5.9. So now what I will conclude today with is a nice result. I am skipping a couple of pages which I'll come back to tomorrow, and that will explain, give the answer to your question. Why is it that this A is not projectable? There is some obstruction. Why is it is not falling through this projection, but its differential is. So tomorrow I will show you. But accept this structure up to now, and this omega, when it is lifted up by this pullback operation, it gives you dA. This is fact. So now I'll go back to the geometric phase. I'll give one last formula, and then that will be it for today. And that is, in my notes, in this section, I've called it subsection C, the geometric phase as a symplectic area. So let me explain what the word symplectic means. This 2 form, which I have defined in this equation, it is a 2 form on the race space. It has all the properties of being defined on pairs of tangent vectors, linear in B prime, antisymmetric. All those properties are there. It has 2 other very important properties. One is its own exterior derivative is 0. That is point number 1. This is called, it is a closed 2 form. And it has one other property, omega is non-degenerate. These 2 properties of a 2 form, being closed and being non-degenerate, define a symplectic structure. Okay, that's very, very important. A manifold is a symplectic manifold if it is possible to define a 2 form on it which is closed and which is non-degenerate. Non-degenerate, it's an algebraic property. I will describe it tomorrow, I'll explain it, but these are the 2 key properties. This closure is actually quite simple to understand. When you go back to Maxwell equations, you know the source-free Maxwell equations. These are the set of Maxwell equations in which the sources do not appear. Usually we say, if this is true, that means what? Divergence of B is equal to 0, and whatever the current independent other Maxwell equation. We say, if this is true, then F can be written in terms of a vector potential. That is how we normally argue. Of course, there are questions of topology and connectedness and so on. The closure of this 2 form is exactly a statement of this kind. If F mu nu was only given to be antisymmetric and you construct this expression, what are the properties it has? It is a 3rd rank covariant object, correct? Moreover, it is completely antisymmetric. So it is a 3 form. And one half of Maxwell's equation says this is actually 0. That is very similar in spirit to this statement of being a closed 2 form. Non-degeneracy is an algebraic thing. I will come to it somewhat later.
So, omega is non-degenerate. Does it mean that omega defined at rho 1 and omega defined at rho 2, they cannot be?
It's a property possessed by omega at each point. I can say it in words, but I wanted to not overload you. But if you're willing to take the burden, I will do so. What does it mean to say omega is non-degenerate? If at a point rho, if omega B prime B is 0 for all B, it can happen only if B prime is also 0. Non-degenerate means omega B prime, this vanishes for all B if and only if B prime vanishes. There is no B prime for which this is identically 0 in B. That's a non-degeneracy. But anyway, we'll come to it later.
But omega need not be an exact form.
For that purpose, no. That's an independent, not exact, closed, not exact,
yeah.
closed,
Yeah.
closed. This omega, in fact, is not exact in the quantum mechanics context also. If it had been exact, there would have been something. Right. Very good. I'm glad to see that you caught the spirit of it.
Because it is not, that is why the abstraction is there.
Yeah, right. So now let me just show you this, and that will be a nice conclusion for today.
So,
Yeah.
when you convince people that omega is really not degenerate, you would have proved that every ray space is a symplectic.
Exactly. And this is, okay.
Yeah, also I think that's why Berry called it a monopole. It's like
In the
so,
sense?
but, I mean, the reason why Berry drew the analogy with the monopole is probably this, that it's a closed but not exact form.
Not really, because you know, the Berry example was in 3-dimensional space. Symplectic manifolds have to be even dimensional.
But on the sphere,
He didn't say so. He worked in 3-dimensional parameter space. All the construction was there. Maybe you can call it monopole. Maybe.
You can put, but I mean, if you
Yeah.
have a hollow sphere with nothing
Yeah.
interior,
Yeah.
I don't know to what extent the further things can be added there. There's no compulsion.
Anyway, let me show you what is meant by this. Now, we have seen from Samuel and Bhandari's work, if I take any open curve in ray space, I can define a geometric phase for it. And what is a prescription? Take the endpoints of your open curve, go back by a geodesic. Then you convert an open curve into a closed loop, and then you use the definition. So, on the other hand, if from the beginning I had a closed loop in the ray space, well, I don't have to go through this operation. I already will know how to define the geometric phase. So it means that I may assume without loss of generality that I am dealing with a curve in ray space which is closed. If it was not closed, I will use the Samuel Bhandari prescription. So I will assume that it is the boundary of some surface, 2-dimensional surface in ray space, spanning the curve. Then for definiteness, let me take a lift which is also closed. And so let me say this is the boundary of some 2-dimensional surface in the upper part of this construction, up in B. All right. Under these circumstances, what is the geometric phase associated with the C in the ray space, closed curve? So I am making use of a lift which is also closed. I mean, the endpoints, there is no gap, just for convenience. So now you know this consists of 2 parts, a total and a dynamical for your lift. This one I have adjusted to be 0 because I say C is a closed curve. So this is not there. And what is this? This is the loop integral of my one form, A up there, only dynamical. Now I do the thing which Berry hesitated to do. You can use Stokes' theorem in any number of dimensions. This is always equal to the 2-dimensional integral of the differential of A. This is an expression written in the machinery of the space B. And this is Stokes' theorem in the language of differential geometry. You can have a space of any number of dimensions, minimum 2. There is no difficulty in principle. You have to get used to notations and conventions and so on. And now you can say, because this fellow comes from a 2 form which exists at a deeper level in the ray space, this is also, it is equal to the integral of this 2 form omega on the surface in ray space spanning the interior of, you have to draw S in any way so that it has a given boundary. So here is the most general meaning and expression for geometric phase. Really amazing. It is just an area computed in the language of symplectic geometry, 2-dimensional area. This is something we are familiar with in classical mechanics at a somewhat advanced level. This is called the Poincare invariant. Areas of dp, dq in phase space across two-dimensional surfaces. So it's quite amazing that here is the nature of geometric phase revealed finally with all this machinery. It is a symplectic area. It is the geometric phase which appeared is a solution to Schrodinger's equation in the adiabatic approximation. This is what it is. What a long and nice journey it has been. So the fact that it is an area, it is computable in this way, this I can say, it reveals to you the intrinsic nature of geometric phases. Whether it is quantum mechanics or classical optics, it doesn't matter. This is the meaning. So if it is relevant in quantum mechanics as well, it tells you that the fact that race space is a symplectic manifold is important for quantum mechanics, which has not generally been recognized or exploited very much up to now. Our friends from Italy, they are great experts in this. The people who had visited here last month, Marmo, Morandi, all these people, they are very familiar with this. So to say that the race space is a symplectic manifold, what does it mean? It is like the phase space of a classical mechanical system. Huh?
That's a link with the...
Yeah. That you can take functions on the race space, you can define Poisson brackets among functions, it will obey the Jacobi identity. In principle, you can do classical Hamiltonian dynamics on a quantum mechanical race space, if you want to. Now, what role it has to play in the quantum to classical limit operation, this I don't know very well. I would imagine that it might, you know, this WKB approximation and so on. In textbooks, this is never, in the traditional textbooks, this is not brought in. So you take Schiff for Landau and Lifshitz, all this structure of race space is not there. But I would imagine that in more modern treatments of this semi-classical limit of quantum mechanics, such ideas are very important. So in a way, you can say geometric phase is bringing you to this kind of link between the two. So I stop at this point. I was very keen to show you how this is, how it turns out. So the two comments about this I wanted to make is, one is that Stokes' theorem is available in any number of dimensions. One should not be, who is afraid of Stokes' theorem? You can say it like that. The other point I want to mention is that in the Samuel and Bhandari paper, they do show that geometric phases are integrals of a two-form omega over two-dimensional surfaces. This statement is given. Unfortunately, they do not recognize or they do not say that this omega is non-degenerate. Therefore, they are not able to say it is a symplectic area. Maybe they were, I don't know. So you can read their paper carefully, keeping in mind my comment about it. As far as I know, the use of such an expression for geometric phase is given, but if until you establish that omega is non-degenerate, it is not a symplectic manifold. Of course, they can call it pre-symplectic manifold, right? Just a little distance away from a symplectic manifold. Okay, let us stop at this point. If you want any